Hey guys, this video shows the Hydra presentation at the People First conference in Berlin. Hydra is the backbone of Libertaria's vision of a decentralized, federated network of blockchains and other distributed ledgers all working together secure each other. The Hydra Ledger will use revolutionary technology based on the AlgoRAND consensus algorithm to provide absolute certainty about transactions. Have fun!
We're about to start a very special presentation by Arpad on Hydra and AlgoRAND. But before we start, I think Marcus wants to say a few sentences, right?
Oh yeah. Well, just personally here in front of this audience, this will be a technical presentation, and if you saw the one in the morning, then you know what's coming. This Hydra project is something that is going beyond the normal blockchain technology that you know from blockchain 1.0 like Bitcoin. So what we are here developing and presenting you is technology of the next generation. So if you ever wanted to know how blockchain works, you probably would bet on a train that passed a long time ago. You should really look into this. This is the technology of tomorrow, and this is what we're doing here. And so thank you, Arpad, and hope you enjoy it, and you can follow it, and it's not too technical for you, but we are recording it, and you can watch it several times at home. Thanks.
Thank you, Naman. Thank you, Marcus. As Marcus said, and Ziggy yesterday, this is the third technical presentation, and as I told Marcus, I'm here to make technical look sexy, and math look sexy, and consensus look sexy. So, first, maybe let me demonstrate quickly a little bit about consensus. So, let's start with some voting, trying to get consensus on these things. How many of you think Hydra is a connotation with hydroplane, because we fly in the air and do not dive but float on top of water? 1, 2. Thank you. How many of you think Hydra is for water in itself? Okay, close enough, still 2. How many of you think Hydra is the mythological figure? You call it water? Thank you. Quite good. Okay, next round. Let me ask again. How many of you think Hydra is the mythological figure? So some people change their mind. So we are getting to supermajority, right? How many of you think AlgoRAND stands for Albert going crazy? That's quite good. How many of you think AlgoRAND is just a random algorithm? Close. And how many of you this is better. How many of you think AlgoRAND is a algorithm that uses randomness and was invented by a famous professor, Mercury? Getting there. Next round. So it seems that I should ask this question again. How many of you think AlgoRAND is invented by Mercury, the famous professor? I give it supermajority again. So, now last question. How many of you think this is not a very good model, what I did, for cryptographic consensus? Thank you. The problem was that this was not private, right? So we saw it, not only myself, but even you. And the other thing is that, in some sense, you used the content, whether it is indeed true or not, what we are voting on, right? So this is not what's happening in consensus and democracy and those kinds of things. So let me start with that. So, as I said, my name is Arpad Slavik. I started with Libertaria in December. Sorry about that. So let me give you a short outline what to expect. So I will briefly discuss the high-level idea, concept and goal with Hydra that was already presented briefly by Vicky. Then to highlight the key features, and then switch to consensus again, because consensus we need to get the protection in our cryptographic world. And I would like to show you the differences from different things. For instance, how is it different from Bitcoin, if some of you know. And also, we already see some differences. We will differ from Mercury and the original AlgoRAND, unless they change their mind and follow us. Then I would like to show you AlgoRAND in main steps and have a demo simulation. This might be misleading because I'm not ready yet with the simulation and the prototype code, which I write in Python, but this is a demo of the demo, how it will look like. So Hydra. As Vicky pointed out, what we want to call Hydra is basically a federated network of distributed ledgers. And because we can imagine abstract and can imagine a lot of things, we would like to step away and say anything we want to record, not only transactions or money and those things. So in general, any journal that is depending on the order of events, how they happen. So therefore I will maybe change journal, blockchain and these types of things in my presentation. And as Vicky also showed you, maybe not all of you were here, but the basic architecture we plan to have is to have parent journals. Of course, one of the parent journals we plan to have our Hydra in itself, and child journals as well, where child journals would be protected by parent journals. So in graph, this is something like we imagine it will look like. And all behind this federated network, there will be this Hydra protocol, and that will enable us to do several things. And maybe easier to explain from the child journal's perspective, all of them will be secured by some parent journals. So we will do the first parent journal, the Hydra one, on the Hydra federated network, and we hope that everyone will choose that for secure their child journals. But if someone else implements a child journal that raises to be a parent, then people, if they like that more, they will choose that parent as a protection. That's fine, because we are open, of course. And that's what I wanted to have here. And we hope to be flexible as much as possible, so if people change their mind, or communities, or then they can even switch these parent journals, their protection. What we want to provide with the federated network is to have an interconnected community ecosystem. So the Hydra protocol will enable these child journals and parent journals to interact with each other and reach anything they want within that. And this we want to provide by the Hydra parent journal by default. And there we will have the interjournal protocols that will enable that. And of course, going back to economical value, these child journals will most probably, a lot of them have their own cryptocurrency, and with this Hydra parent journal we would like to provide easy and cheap atomic swaps between these child chains. As Marcus likes to put it, if Bitcoins comes to be one of the child journals, fine. So, in another perspective, the key features we foresee and we plan to have is the Hydra Genesis templates, where basically anybody can create their own blockchain for their own purposes, for their own communities, and of course have their own crypto tokens. And we would like to gradually be able to allow consensus options to choose from. So hopefully AlgoRAND and IOP, which will be the first two, and anyone joining, those if we can integrate them, people will be able to choose from that. Further in the future, we would like to add governance, voting, smart contracts, options, and these types of things that you can choose from, so you can create your own community as such. And the federated network in itself, with these parent journal, child journals, is already a natural scaling factor, so that is a powerful thing. So both locally and globally, this provides us with a good scaling by design. And technically speaking, written in Rust stands here for will be written in Rust, because you probably code that I am still in the prototyping simulation phase, doing it in Python. But when we are able to move to productionization, then it will be in Rust for the same reasons as the rest of Libertaria and project's work, is because of the secure things around memory handling and overflow. So let me switch to the real topic, again back to consensus things. So the consensus, we need to have a distributed, open, trustless protection of the network we have. And our parent journal, the Hydra one, we plan to have our version of AlgoRAND as the protection algorithm there. So we might call it, Hydra AlgoRAND. This is what I would like to show you in some details. And the benefits we already foresee and know that will be there. That AlgoRAND, as even originally designed, is indeed decentralized. So there is not expected to be concentration of power as in Bitcoin. It's really trustless. So different type of algorithms use some round robin without random things where malicious people can guess and attack upfront. This is not possible for AlgoRAND. Real equality is given the stake weight, so you might guess already that it's something like a proof of stake type of consensus we want to have here. But in some sense, this is able to provide the same idea that Satoshi wanted, that okay, if someone has more money, it's fair if he gets more chance to win things, but only to the extent how bigger he is. And this is by design like that in AlgoRAND. And this was planned to be really able to do transaction finality. I don't know whether you can appreciate that or not, how much Bitcoin transactions you did, but maybe a lot of you know that even the suggestion is to wait at least 6-7 blocks until you start to think that your transaction went through. Here, AlgoRAND is designed to really not have forks, as I say here, so therefore we can faster achieve real transaction finality, because if there will be no fork by design within our main chain, then we don't have to wait anymore. If we say something is final, then you can put a stamp on it. similarly, it's scalable not in the sense I mentioned the high level, but scalable also because how it's designed, because we can keep the important part of the consensus limited because of randomness, and it's also secure because it was designed to be secure. So let me switch to showing, or at least highlighting, some differences from Bitcoin. I already mentioned that this is kind of a proof of stake approach as compared to proof of work, which we know, I hope a lot of you know the disadvantages of proof of work. And I would also highlight the difference. The randomness used in AlgoRAND is not random in the most precise way, and that's good because then we can do verifiable randomness, and that comes to our benefit. And not only because of it's pseudo-random, but really something you can replicate when needed. So this is a very good thing. And the same guessing type of thing in Bitcoin would be the computational power, because basically that power is used to win the guessing game. The other difference is, so there are no real roles in AlgoRAND in the sense that Bitcoin Evolve or some other competitors where there are specifically defined different roles. So there are no miners and rest of the world, or no selected voters or delegates and all those kinds of things. And even more, even during the algorithm, the built-in roles can be switched and replaced, and that's additional power and security of AlgoRAND, that if someone does something that is important for the security, immediately he can be exchanged to another person who can continue from there, as compared to Bitcoin. Difference we already see from original AlgoRAND, or as we know it. We believe that so AlgoRAND, they do not really do rewards and incentives, but assumptions about network connectivity and those kinds of things. I believe if we put initiatives in, and then even this network availability thing will work more naturally, and this is what we really want to add. Maybe they will also add it, but as of now I don't think they are well prepared for this or upfront. And the thing that I almost do not understand why they say that the problem during the work of AlgoRAND is that when somebody does something important for the protection, then big, powerful, malicious guys can already attack him because that guy revealed his identity. So I will try to demonstrate you that we do not need that, so we can keep this private. This might be too technical, but let me try to summarize. So there are rounds in AlgoRAND which aim to create a block. In every round we want to create a block, and every round compounds of phases, and in each phases we have steps, and the basic idea is first phase should be the block proposal, or how we would call it in the new world, maybe journal item instead of block, so if it's not about transactions. The point is to have a random small number of users elected by random who are eligible to propose this new block, the next block. And then the thing is that based on cryptography and how AlgoRAND is designed, anybody can only tell about himself or herself whether they are eligible to propose a block or not. So this is a good protection against adversaries, malicious people, because they cannot guess up front, other than maybe guessing based on the stake size. But as they do not know where that stake sits, maybe it's not that bad. And they all will propose a block and send their proof of eligibility. They sign some messages, and then everybody can say, oh really, I trust him, he is really eligible, because there I can see the message which proves that he was eligible. And then, in the end, only when they start to receive these proofs and blocks, everybody can realize who is supposed to be the winner out of these eligible people. Even the later winner will learn retrospectively that he is the winner. And this is basically a hashing function, also kind of random, that will provide the winner block who should everybody start voting on. So this is a deterministic in that sense. A similar, little bit more convoluted case because of protection for the next phase, where we would like to have the voting part, which we played in the beginning, where committee will similarly be chosen by random, a small number of them, as I mentioned. This is basically the not everybody is voting and not everybody is proposing the block. This is additional scaling benefit of AlgoRAND. And committee people, similarly based on cryptography, can tell for themselves whether they are part of the committee and whether they should vote or not, whether they should select a block for voting. And then, because of the possible convoluted and very clever attack possibilities, there are several steps where we would like to reach to a consensus, assuming that maybe we are under attack. And this consists of a limited number of loops, not to have an infinite loop and never end, of gossiping votes, counting votes, and even adding an additional random if adversary is quite powerful and close to winning, and she could direct the first two almost deterministic parts, then we flip a coin and vote based on that adversary cannot guess up front. And then the powerful thing comes because of the design, that at the end, when we are finished, then we can even decide whether this is as big a consensus that this is a final block already, or we do not know yet. We have to wait a few more. When we get a final block again, then this tentative will become final without having to change. So this comes from the techniques and everything that is invented in AlgoRAND. And there is an additional phase, because this is very powerful if we have quite an available network, but even if adversary or outage or something makes our network not really available or pause, this means that messages do not go through as we wanted. Then there is a recovery phase also where basically a fork is starting to happen, but we stop a bit and make a round of votes which fork to choose, and therefore we are back on a single fork or branch or that type of thing. So this is what I wanted to explain you about in general, and then to demonstrate you a couple of things, how it works, if you are interested. So as I said, this is a demonstration of the future simulation that will come out of the Python code we are working on. So this part, some things I want to show you around the gossip network, to explain how it works in general and how can we achieve that privateness that even AlgoRAND people did not notice yet, it seems, or they keep it secret. And some interesting thing about messaging there, what I call additional effectivity related to gossip network. Then I will show you some assumptions or models how I think we can have a realistic simulation that will not only demonstrate that it works, but maybe we can fine-tune it to have to try several scenarios, several parameters, and those kinds of things realistically. And I also wanted to show you a little bit about the phases I was talking about. Maybe that would be easier to understand if I demonstrate it to you. So about the gossip network. So network, let's see, it's a cloud, and I don't know if you know from Bitcoin, but there is, if someone does not know anybody within the network, he can go to some central type of node. This is a curse word here in our community, but still. And you probably have noticed that a new node wanting to join can ask for peers, neighbors from someone, and then he will be delivered some people who that new node is supposed to send gossip the messages towards, and from whom the node will get the messages, the information from the network. So that node becomes part of the network after this is set up. And by the way, this is important as in Bitcoin. So this is as in Bitcoin. You probably heard that this is something like 7 connections, 7, 8 connections, and those kinds of things. And we want to assume open network, so anybody can join if they want. So that's why this is what we plan to have. Then let me demonstrate you how the gossip works. So let's imagine then from node, the new node, let's say, or some selected node, a transaction idea or transaction comes out, and then let's see how it goes through the network. So this is representing the transaction. He's supposed to send it to his out peers, and it goes somehow in the network and is coming back. Of course, when it comes back, this node can know that, okay, most probably everybody, or at least everybody honest knows this transaction, so he will not relay it once more, and similarly goes for others. So if something they hear as a gossip, let's say a transaction, they will relay it to their peers, but when that message comes back, they will not relay it anymore because they did it already. And that's when it's done, and it's quite fast. Now, let me show you why we are not exposed to privateness concerns. Because previously I said that it was somebody within the node who created the transaction. So we could say that these people knew that it was coming from here. But if you think about it, as I said, they are all relaying, so they will not know whether this came from this, because from their perspective, I don't know whether you can spot from their perspective if there is a difference if the message came from this node. Could you tell? Okay, so the reason we can do this, so what I'm trying to say is that these people cannot tell whether that message was originated by this node or that node was only relaying it. The reason is that this node is not signing it, not saying that, okay, this is my message. The message is signed by the users within the node, and let me try to show you that as well. So a node within inside, sketchy. So this here represents the blockchain. We have a genesis block, and this is the chain, so the blocks are linked into each other. This is something that we always assume is kind of public, so in a way, all nodes have or can have, or we would like to have the same or similar copy of this public information. So that's what the aim of the consensus is, to have an agreement on this blockchain or this journal. But then we want to have a lot of private things within the node. And the most important things are our private keys, right? So the secure keys. Even the public key and the secure key are private to us, and the amount of how much money we have there, we can have more. The reason I say the public key and the amount is also private to us is because on the ledger, anyone can see what transactions happen. So here we see public key. First, it sent money, public key received money, and anyone can calculate what amount public key number 1, public key number 2 has, because it checks the history and adds up, it tracks, those kind of things. What they do not know is the information that these are within this node, because even that is secret. So that's why the previous thing worked, because some secure key signed the transaction saying that it's sending money, but after it left the node, no one else can tell that that secure key which signed that message is sitting in this node. And basically that's what I wanted to demonstrate to you why it works, why it should work. The other thing I wanted to show, maybe even more technical, so transactions this is similar to Bitcoin, some of you might recognize. So public keys are sending money to each other, that's what's in transaction messages. And blocks, or as we might call it, journal items, consists of these transactions. That's the goal, we pack it in blocks. And what else we have there in general? So these are the transactions. And we have the link to the previous hash, that is why it's a chain. And we have some kind of proof. In Bitcoin, this is exactly the proof of work. In AlgoRAND, it will be different. But structurally, it's the same. You might see the empty space here. That's not a mistake. So there are some specific different messages. For effectivity reasons, we can introduce some proof messages as well, which are very small ones, which are basically a proof, the same proof that is here. And this block hash is basically the hash of this block, not the previous one, but this one. And we want to be able to send this proof separately from the block as well. And we will also have in the voting phase, the committee voting phase, vote messages when you can imagine, such as the proofs are there, the same proofs with the proof and the reference to the block, and even the previous to the linked block over there. And the important thing is here that this proof is much smaller in size and travels much faster in the network than these block sizes, because of course there is always a trade-off between how fast the block can travel in the network and how much information we can put it into it. But we tend to want to have it bigger, to have more transactions, right? And I can tell you that we want to have some other types of messaging-like things there. So for instance, from peers, it's okay to ask something like, oh wait, I don't have this block, or just such, can you provide me the block which has this hash? If you think of it, it's important from bootstrapping perspective. If someone new joins, he needs to be able to get the whole history. This is the same as in Bitcoin. And the new thing in AlgoRAND related to the proof is that within the block we don't have a believable proof of work which is good enough for anyone new to believe that it meant something. It's really the true history. So therefore, in AlgoRAND we need something like a list of votes that people can rewind history and check for themselves. So the list of votes back in the day in separate rounds. And that's basically the list of proofs that's also floating around. And therefore, if we have the block proposal phase, let's imagine these two nodes are in the block proposal eligible people, and they propose their separate blocks, and these proof messages and the block itself will be sent separately, and it will travel faster. So let me show you that then within the network, if someone is able to see the proofs already, it does not have to send a block which he knows will not win. So let me try to demonstrate that. So it travels faster, gets to M3, and this guy does not even have to send the blue block, because he already received upfront that red will have more chance to win. So only the red block needs to be sent. This sounds like a big improvement as I put now, but this is in exchange for the additional block proposing. I mean, in Bitcoin only the fastest wins, so in general it's basically that block that needs to traverse the network. Here we want to have more block proposers, so this is getting back to similar terms, because we are able to make it more efficient within the network. Just let me see. Not bad. So something about simulation. So I have been thinking of node creation models. As I said, open network, and nodes can join freely, and also the transaction creation model to be able to calibrate it to real life, and even adversary models we can put into the simulation to play around with it, which means something, not only playing around. And so therefore I would like to have a random process for the creation intervals for node creation. So basically this is something like how often we want the nodes to be created during time. So in some sense we are doing some randomness, flipping a coin, and then a new node pops up, then faster, slower, random processes are able to give us, and we can calibrate this to the data if we have. Transaction and user creation model, this is more convoluted because it's a little bit more details we have to work out. So imagine these nodes. Okay, I already see a mistake. So this is a compound random process. So one thing, okay, we want to choose a node within the simulation. So this is not revealing in real life, only from our perspective, who are trying to simulate the network. We want to select a node where we will pick a user who will be sending money to some people. So this is what we want to achieve. Then we want to select a user from there. Let's say it's selected together with its available balance of money. So we select within the node with a different process. Then let's have another process or random number saying how much money that girl wants to spend. Again, random. And then we also determine how many users or receivers we want to have, and within that we want to have how many of all the existing ones, how many users we want to create to fake a transaction kind of, and how many new users will be created, as if this was a light wallet or a friend who is not part of the network but created an address and wants to receive money, and I am willing to give them. So this is all part of this. And then we even select these receivers to be able to tell which users will be sending this. As you can see, the colors, I try to show that new self-user turns out to be somewhere within the same node. So if it comes from here, or we will select it from here if we decide to want to model this as well. And then it's easy to split the amount as well, who gets how much, and then I believe we have a quite realistic type of model for creation and quite compound. And adversary, let me say, so the malicious guys in AlgoRAND are quite powerful. I did not really see as powerful adversary model or assumptions as Mikali and AlgoRAND guys did. So what I think we could do is to have a random process of just having a pick and point selection that adversary is able to attack a node and take over completely forever. I mean, for simulation, this is definitely good. In reality, if we are hijacked, we would create a new node and maybe wouldn't be able to get back what we have, but this is how I think we can have. And the adversary, so therefore we select this guy is out, maybe this as well. So similarly as the node creation, but of course you can feel that if this node creation intensity frequency is faster than the new honest nodes, then it will not be good. We will most probably die as a network, but this is what we want to be able to measure and safeguard against. And then you can imagine big power. So, for instance, within AlgoRAND, if a malicious guy or hijack guy gets to be a winner, it can trick the system, at least make it worse if it does not say anything, does not propose a block, or if it becomes committee member, it will vote on an empty block, not to be able to progress in the system. Or related to messages, it's not good if messages are late, so they would delay the messages as much as they want before they are busted. So everything we'll imagine and we'll play around with this, how much and what strategies they can use and still be good. Okay, I think I don't remember when I started. Do I have time?
5 minutes.
5 minutes with questions?
With questions.
So then I think if you are interested to see similar demonstration of AlgoRAND phases as well, we can take it offline to a separate room or something I can show you. Otherwise, I think we should open to questions.
Yeah, I think it's good to have a question or two just really quickly from the crowd. It's a very technical presentation. After, at the end of the day, we'll have a panel here with also with Marcus on stage. We'll be able to ask some more of the visionary questions. But yeah, one or two technical questions from the crowd perhaps. Anyone? On AlgoRAND? In the back.
So you will collect the votes, even the loser votes, all inside the blockchain or whatever you have, John?
Can you repeat?
You said that the users can request to be resend the votes from previous blocks, so that they can validate. So actually all votes would have to be recorded?
Yes, yes.
Okay.
I mean, we can work out the details about that. We can either put it also on the journal, on the blockchain, or have it separately protected. But maybe it's easiest if we also put it on the blockchain to have it safe. Because I was not able to show you the finalization of blocks, but after we have final blocks, then it's safe to have everything there up until that.
Oh, okay. Yeah. Thank you.
No problem.
All right. Any other questions? One here.
Could you highlight any key differences between the original AlgoRAND developed by Silvio and any changes you're seeing in your implementation? Just highlight those again.
To summarize, I mean, so let me try to say it in other words. So Mikali and all his team, what papers they presented are quite honest about all the technology and details and everything, but even when they did implement it, one or two versions of their AlgoRAND, that part is not public, right? So I can only tell the difference from theoretical perspective, and that's what I try to show you. They stress a lot of time this privacy concern. That is the difference. I don't think that means that they assume that people know or have to know who sits where and who has how much money. But I believe, and we believe in Libertaria, that no one needs to know what keys and addresses I have within my wallet. So they do not even have to know what is the total amount of my stake. Randomness will select it fairly based on the amount I have, but no one needs to summarize it up front or tell it. It's not based on that. Randomness will select because the majority or the big portion will be selected fairly. This was one. And the other is related to rewards. So up until now, they did not really want to care about rewards. Mikkel even said that they think this can work without rewards and incentives. We don't think that, so that's why we plan to add rewards, definitely. For instance, for block proposal, as if the random type of mining can be rewarded. And that's how we can hopefully achieve that everybody is incentivized to be online, to participate.
Okay, thank you. Thank you for your presentation.